Let me try again.
This meeting is being recorded.
Can you hear me now? Is that better? Can
I
others
can
hear?
hear you fine. Mary?
Yeah, I can hear you as well. Mary, there might be a connection issue on your end, possibly.
We can hear you.
Oops.
Is she still there?
I'm checking my speaker
Oh,
and it's now at the max.
How does that sound?
Okay.
Okay.
Yeah.
I'll talk loud. My
Not
wife,
as loud as
my
everybody
wife can
else,
tell
though.
when I'm on a Zoom because I talk really loud, she says. You tell me when to start.
well, why don't we get started? I'm just going to do a little brief intro. Greetings from Friends of North Point and the Lakeshore Natural Resource Partnership. LNRP has been fundamental in coordinating, funding, planning, and implementing the North Point Bluff restoration, as well as many other projects. I recommend checking them out if you haven't been to their website. I think pretty much everybody on right now has probably been to lnrp.org, but I recommend it if you haven't. We welcome Dr. Elmo Rawling, and Dr. Rawling is a UW professor and Quaternary Biologist with the Wisconsin Geological and Natural History Survey. And you can see his title right there, Impacts of Lake Level Variations on Wisconsin Beaches and Bluffs. And I'll turn it over to Dr. Rawling.
Thanks. You can call me Elmo, please. And just a minor correction, geologist, not biologist. It's okay. Yep. And that word quaternary always trips people up. It's our formal title. It really just refers to the ice ages. So the last 2 million years of Earth history. Most of what I do is for the survey is work on mapping glacial deposits for the state, but I'll talk a little bit about that on the next slide. So yeah, I'm with the Wisconsin Geologic Natural History Survey. We're within extension at the University of Wisconsin-Madison. And today I'm just going to talk a little bit about some background about the Great Lakes, the bluffs, impacts of lake levels on bluffs and beaches and sandbars. And then I'll talk a little bit about ice if there's time. And a lot of this will be research that I've serve on committees of various students. So a lot of the work I'll show you today is work that others have done, but I'll credit them. I'll let you know who they are as we're going through the talk. So we've just been through one of these big lake level changes, and so it's probably pretty timely, and everybody has sort of probably can remember like the last 5, 6, 7, 8 years, what's happened to the lake. And so why is that happening? What are the impacts? That's what I'm hoping to talk about today. I've also broken it up so that we just can have a conversation between each of these sections, so we don't have to wait till the end for any discussion, and feel free to interrupt anytime. Let me see why my...
No, it switches up. People there now.
There we go. So just a little bit about us. There's our website, and I can, you're recording, so you can find this on the recording, and I can also turn this into a PDF, Patricia, if you want, and you can share it that way too. The Geologic and Natural History Survey has been around since 1897. It started out as a state agency. It was moved into the university system in the 30s. Things like the Department of Transportation came from us, used to be associated with us, but we're really the states. Most states have a state geologic survey. We're different from the USGS, the United States Geologic Survey. So we are focused mostly only on Wisconsin geology, and we have about 30 full-time people who work on groundwater, so aquifers, aquifer characteristics, and then a lot of geologists who map either the sediment, the largely glacial deposits in the state, and the rock, the bedrock below that, and with the goal of helping, primarily helping groundwater researchers understand that aquifer system better. We have some IT and GIS staff and administrators and archivists. We have a large collection of core and samples in Mount Horeb, and there's a whole facility there. And we are the official archive of geologic information for the state. as I mentioned, I study mostly work on the glacial sediment in Wisconsin, but then as a professor at Madison, I also interact with some of the members of the geoscience department, so they're separate from us, and they're graduate students, and that's the kind of some of the research I'll share today. All right, so just basics. I'm sure some of you know a lot of this, but I just wanted to run through it so we're all starting from the same place, right? You know, the Great Lakes, obviously, Sheboygan somewhere under that star. We're somewhere in the mid latitudes, and substantial amount of shoreline, 9,300 miles of shoreline, something like a tenth of all the shoreline in the lower 48. Probably more importantly, 20% of the world's fresh water is here. That's some 5,500 cubic miles of water represented in the Great Lakes. And of course, if you're from Sheboygan, as I am, class of 89, Sheboygan South, right? It's the Malibu of the Midwest, although I don't think they were surfing there in the 80s when I was there. But of course, since I've left there, they have, right?
Sheboygan. Heard that.
Sheboygan.
In 80.
And the Great Lakes, you know, they're sort of sometimes called the third coast, and that's sort of to sort of differentiate us from the ocean shorelines. It sometimes, unfortunately, is also sort of third in terms of like funding resources that have been federally allocated for shorelines. And so a lot of times people will try to compare us to the oceans, but we really are a very different system. And we're really very different in the way that water levels fluctuate. So this is a short-term time series of about a month at Green Bay. This one I couldn't change. It's still in metric. I'll use feet for most of this presentation, but that's like half a yard. If we're thinking about Green Bay, that's the distance here, half a yard this way, right? And that's the fluctuation just measured at Green Bay over time for a month, right? So about half a yard or almost a yard of variability, 3 feet, just for various reasons, right? And pretty noisy, not really predictable, versus something like this. This is Key West and water levels, and they're very periodic, right? That's the tides coming in and out every day, right? And there might be some sort of fluctuations depending on swales and high and low pressure systems on the oceans, but you're really looking at something quite different in terms of levels. If we want to look longer term at water levels, we have here in feet now the long-term record. So this red line is the historic average of the Great Lakes or Lake Michigan from 1920 to 2023. And what we see are periods where it's high, and about every 10 or so-ish years, it goes up and down. So there was a real high stand in the 1930s, the 50s were high, 70s were a real gradual rise and a really prolonged rise. That was unique about that one. 80s were the high record. I don't think we quite got there this time. I'm not sure, I don't think. And then 90s were really short. And then we went into a period of almost 20 years of really low lake levels, and managers and others who think about resources along the lakes were almost wondering if we had to think about a new average, a new red bar, right? Because lots of infrastructure got moved and people got used to like wide beaches and all sorts of things associated with lower lake levels, and then of course it went back up. And you can contrast that with sort of a similar time series of the oceans, and they're kind of steadily rising as they change, although in inches here, not in feet, right? So 6 feet or 7 feet of variability over sort of 10-year time scales along the Great Lakes. And of course, this makes news, right? Lake Michigan Huron hit a record low in February of 13, and then, maybe 8-10 years later, record-breaking highs again, right? And of course, this causes issues for infrastructure, ecosystems, management of those systems, both in the public and the private sector. And that's some of the stuff that I'll talk about today. So again, that recent water level fluctuation, somewhere at 2013, all of a sudden, the lake kind of went back up. And that's sort of what I want to talk about in this first section is what's controlling these highs versus these lows. Why are we getting this sort of quasi-decadal cycle within our water levels in Lake Michigan? And basically there are like three controls that we can think of for the Great Lakes and over long periods of time. So if you're most of what I do is think about the glaciers when they were here on that sort of tens of thousands of year cycle. And so some 25,000 years ago, the upper Midwest in Canada looked like this. We had a big ice sheet sitting over Hudson Bay and coming down into Wisconsin. And that's a lot of weight. And that actually pushes the Earth's crust. And when that weight is gone, that crust rebounds. That's what this isostatic rebound word means. And if we can actually measure that with GPS systems today, and the reds here represent areas where the Earth's surface is rising, and blues represent where it's kind of going down relative to that. And but very little. This is millimeters per year, so just a little bit. Although 10 millimeters per year up here in Canada, and if you look at Lake Superior, it's actually rising in the east and going down in the west, and so that lake level will change. Right, the parent lake level will go up on one side and down on the other side as the land elevation changes. Although that's short term, and that's not controlling this cycle that I'm talking about, this 100-year cycle of up and down. So the other thing that can control, then we got to think about our outlets. What are the elevation of the outlets? And here are the sort of elevations of the various lakes. So Superior is a few meters above Michigan Huron, which is above Lake Erie, which is above a lot above Lake Ontario. We have the falls, Niagara Falls between those. And of course, we can put dams at those outlets, and we will artificially control the lake level, raise it, and maybe keep it more steady. There is a structure on Lake Superior. It's partially controlled. There is no structure on Lakes Michigan and Huron. They're a wild lake. There's nothing controls their, we don't control their lake level, and they're essentially one lake. They always get lumped together as when you think about levels, because there is no difference in their elevation. So this is the distribution of the drainages, right? That goes through the salt straits from Superior down into Huron. Michigan and Huron, that connection is actually fairly wide where the Mackinac Bridge is, and that's not an outlet. There's no change in elevation between those two lakes. So they have the same elevation. They go up and down together. Their elevation is ultimately controlled by the Port Huron outlet, which goes into Erie, and then of course Niagara Falls, Ontario, and out the St. Lawrence Seaway for the whole system. You'll hear when people think about lake levels in the Michigan Huron system about dredging that occurred at Port Huron. So there was some dredging through the St. Clair River, and that was is sort of represented in this graph by things that increase the lake level and things that decrease. So either diversions or dredging, and that dredging really is probably something like 15 inches, so not maybe a foot of elevation change. And that dredging has occurred. Since that dredging has occurred, the lake has gone up 6-7 feet and down 6-7 feet around that average as well. So when the lake is low, you'll often hear people concerned, well, was it maybe that if we hadn't done that dredging, we'd have another additional foot of water, but that's not necessarily controlling these cycles. The outlet was higher for the whole Michigan Superior and Huron system in the geologic past, so somewhere in the last 6,000 years, those lakes used to drain to the north, and they had one common elevation. Lake Superior, Lake Huron, Lake Michigan were all one lake, and there are big dunes in Door County at Whitefish Dunes, and then in Bailey's Harbor area, there are all these little ridges that represent older shorelines that date back thousands of years. And some of those were impacted by these outlet changes over the course of geologic time. But again, that modern system probably set up somewhere around 6,000 years ago. And since then, we've probably been going through some of these more decadal sort of changes. And this is the Bailey's Harbor. There's a nice, if you've been up there, there's a nice trail in this area in a nature preserve. The Ridges, it's called. Okay, so if that's a long way of saying those are things that could control lake elevation, but aren't controlling lake elevation on this 100-year sort of scale. And so what is, and it's probably climate. The answer is climate. And the climate, by climate, I just mean the amount of water, precipitation coming in and evaporation going out. So maybe in a little bit of sense, temperature, but really the water portion. When we think of climate, we think of average amounts of water coming in through rain and leaving through evaporation. And this is this is showing you Lake Michigan, a sort of just a rough depiction of water, how water gets into Lake Michigan, the inflows, and how water gets out, the outflows. And of course, they have to be equal. Otherwise, if the outflows were greater, the whole lake would drain. If the inflows were greater, the whole lake would keep going up over time. And it doesn't, it goes up and down. So there's some small diversions. There's some surface water and groundwater that are discharging into streams that go into the lake or directly into the lake. Those are pretty slow systems. They don't really respond rapidly to variability, but this one is really the thing that can change climatically on these decadal sort of scales, right? And a lot of the water that is in Lake Michigan fell into Lake Michigan from storms, right? I never really thought about this until I started working in the lake system. Even though I grew up along Lake Michigan, I think of lakes getting water from streams more, but these lakes are huge and storm systems go across them and put tremendous amounts of water right onto the lake, just from storms directly. And then the other side, things that can vary going out, really one of the only things that can vary going out is evaporation. And there's not a lot of data on how much evaporation falls directly on the lake. Or I'm sorry, precipitation that falls on the lake or evaporation that comes off of the lake, right? There aren't big rain gauges all over the lake and there aren't big evaporation meters all over the lake. There's one or two that I know of in Lake Superior on some lighthouses out there that are trying to measure evaporation. And so in cold years, if there's a lot of ice, there would be less evaporation, right? And that could cause the lake to go up a little bit. But probably more importantly, our shoulder seasons, things like fall and spring, how dry are they? And if you have really dry air masses in the spring and the fall, then you'll probably can get more evaporation because that warm air can take more moisture off of the lakes. And so it's some combination of how much evaporation versus how much precipitation that's controlling this cycle that I've been talking about, this sort of cycle. And so what I want to do is start thinking about one of these cycles on beaches and bluffs, but this would be the first place where I like have any discussion or if there's any questions before I keep going. Really clear? Great. I'm going to keep going. All right. All right, then let's look and see what one of these cycles does to things like bluffs. And I've got a little bit of terminology that I just want to define before I look at the bluffs, both in this section and the next section, just from sort of the geomorphology or landscape systems, geology, glacial geology, to think about. And that's the thing about like this word angle of repose. And so for any slope, it turns out for any slope with a given size material, there's an angle that's stable in the sense that if I'm a grain on this slope, I'm trying to be pulled down by gravity, but friction is preventing me from going down slope. And if I get too steep, gravity wins and the grain goes down. If I'm too shallow, friction wins and I stay where I'm at. And if I get just the right angle, everything will be stable. And you can see this in this picture here. This is two pieces of plexiglass with some different colored sands, and the sands are always at the same angle. The base gets wider as the sand pile gets higher, but the angle maintains. This is different for different materials. Clay is more cohesive, so that's more, you can have straighter slopes with clay. And wet sand versus dry sand is different. So dry sand, if you try to think about being on a beach and building a sandcastle with dry sand, it's gonna like kind of keep sliding. You'll be able to get a big hill, but it'll be really wide. If you get that just a little bit wet, you can take your bucket of sand and pull it off, and you'll have a nice, right, straight, steep slope on your sandcastle. But if you take a bucket of water and pour it over that poor kid's sandcastle, right, the whole thing melts, right? We've lost the friction and there's no cohesion, and we lose our angle of repose. So this happens in nature too, right? So here's just a Google map screenshot of North Point. And in the fall, I was lucky to catch one in the fall, and that's a pretty stable slope, right? It's a pretty stable slope for a number of reasons. I can tell the angle. I can probably, if I knew what the grain size was, I probably could say, yeah, that's the angle that I would expect for the different strata within that. And it's vegetated, right? There's a lot of vegetation on it. And of course, it's stable because, this road is here and it's preventing the waves from interacting with the base of that slope. But it wasn't always that way. Right? It wasn't always stable. This is something Laura gave me from Sheboygan County Historic Center or Society, sorry, showing the bluffs from Lake Point before the drive, before the road was put in. So that road was put in the 30s, and in part to connect Chicago to, they were going to do a road all the way around the lake. They were very ambitious back then. But also that helps prevent the waves from interacting with these slopes and allows them to become stable, right? So it hasn't always been a stable slope. And this is 1937. This is the earliest air photos for the area. And there's North Point, and you can kind of make out it's really bright along there. It was still a bare slope back in the day. So I always say to my friends who are trying to preserve some natural state on these very unstable systems, well, actually, you got to take all the vegetation off if you want to make it back to its original. But I just say that in jest. I know you guys are doing great work getting the slope restored to some sort of native vegetation. Okay, so I'm going to not just talk about North Point. I'm going to talk about all the way down in Milwaukee County and Milwaukee County, all the way up to Manitowoc County and Sheboygan County, some sites. This is an unstable slope. And what we have here, this is a drone taking a picture, so you get a sense of it's a little weird. You're looking at it from some angle, and there's a tree for scale. And this is a very large landslide that has sort of come out into the lake. More recently, this was 2021, I want to say 2020 or 2021. And there's a lot of different processes that can cause these failures. There's just water running off the surface. A little bit of sediment might come off from that, but then we get these deep, big failures that occur, and sort of what's controlling them and how are they related to lake level changes. Here's some sort of two slopes by the Racine County, just behind the Racine County Zoo. And, one is bare and probably a little steep, and the other one in the back is vegetated. And maybe there's some structures there helping with that, and is more at that angle of repose. But even if we look at this slope, we kind of see a change right around there where it gets a little steeper. And that's kind of what I want to talk about in terms of lake level fluctuations. So, of course, what we're worried about with these slopes, these bluffs, are two sort of things. One, right, is down at the toe where the waves are, and then what's the shape of the face, and then the crest where people might have a house or roads or other infrastructure. And two things can happen. One, the toe can recede. So if lake level comes up, waves can get further in and attack that toe and remove material. If the lake level goes down, material can accumulate there, and the toe can then go out towards the lake. But eventually, this failure, is going to maybe connect to up at the crest. So they're two different systems. What's going on at the toe isn't always felt at the top of the slope, depending on how big that slope is. And the way the failures kind of progress looks something like this. If we have a steep slope, we're going to get failures. Those failures are going to create this nice angle, gentle angle of repose that is stable. And so that would be like low lake levels. Lakes, if the lake comes up, it's going to start to oversteepen just the toe. And then that toe is too steep, so it's unstable, and it will fail eventually. And that failure will get higher and higher up the slope until it reaches the crest. And then the whole thing is steep again, and it can fail again if the lake goes back down. That's the kind of cycle that we're in, and that's the kind of thing we wanted to study with this most recent lake level rise and fall. So we've been also my funding sources, but we were fortunate to get some Sea Grant money and have funded several students and some National Science Foundation money to sort of study this with modern tools, right? So this cycle, we've known this cycle. There are people in the 70s who watched it, people in the 80s, and even people in the 30s watching these cycles and kind of developing these models of how lake level impact bluff erosion. But what we've been doing is using drones with cameras and flying back and forth across a slope, a given slope. And this sort of depicts all the different pictures. And then you can use something called structure from motion, which is a computer model that takes the different perspectives. If you know where the drone is in space and you have some GPS points on the ground that you've surveyed in very precisely, this will use, just like your eye has two perspectives and makes a three-dimensional image for you, it'll make a three-dimensional elevation model just from photographs. And so this is a depiction with the photographs, and then this is a depiction of that computer model of the slope. And we're getting an elevation point every 10 centimeters or every couple inches. So we get a very precise slope model. And that's relatively cheap to do. You can get a cheap drone with a kind of expensive GPS unit. But in the world of surveying, you don't need a giant ship or millions of dollars. You need like thousands of dollars rather than millions. And one of our students, Russ Kruger, did this, and he looked at a bunch of different bluffs. So this is in just north of Sheboygan. And this is 2012. And what it looked like where the slope was gentle coming all the way to the beach. And this is what it looked like in 2018. And the failure surface is right there. And by looking at a whole bunch of different slopes, he was able to calculate that this thing moves up something like 15 feet per year. So that means if your slope is 30 feet high, you're not going to notice it for 2 years. That means if your slope is 150 feet high, like Ozaukee County, where they're really tall slopes, it might be 10 years before somebody at the top knows that there's failures coming from the bottom. And so if you're not paying attention to the bottom, you might not know that's coming. And we could be already through one of these cycles before, so lakes could be low and there's still could be problems coming for the people at the top of the big slopes. So we were interested in sort of an average, that's kind of average, but then we wanted to think about it more through time. And so there's a sort of cycle, seasonal cycle where the lake is a little bit higher in the summers and a little bit lower in the winters. And so we surveyed one site sort of as the summer came on, as the summer came off in the middle of winter, and then as the summer came on again, through an up and down of the seasonal cycle. And then we're able to subtract basically the elevation or add the elevation change between those surveys. So between the first two, the second and third, the third and the fourth, what we noticed was a lot more erosion right after the thaw, right? So we really get most of the erosion occurring seasonally after everything thaws. And that was Chelsea Volpano. She was one of our master's students, and she also some more of her work. She's working on a PhD now. And that got us thinking, well, if it's happening on average, something like 15 feet a year, and through time more seasonally, what about when you go along a bluff and it's really failing in one spot and not another spot? Then there's no like structures or something controlling why that would be happening. And so another one of our students, Colin, did a really detailed study at one of the parks in the Milwaukee County system, where he put field cameras out so he could watch. He mapped where the springs were. These are springs, and did some groundwater. He put wells in to look at what the groundwater was doing, and then did these models to track how the crest was receding and how the toe was receding at that site. And this is probably my most complicated slide, but this is the model that he came up with, and it's pretty clever. It's very clever. And these lakes, bluffs, our bluffs have different units in them. If you go up the bluff, there'll be sandy material from meltwater streams. There'll be material directly from the ice that might have more clay in it. And in these sandy units is where we often find the groundwater table. And if the water can drain through a spring, if it hits a clay layer, it's going to drain out of the middle of the bluff. When that freezes, though, that shuts that off. And so pore pressure is kind of low and the strength of the material is low in the summer. As it freezes, the pore pressure increases, but that frozen layer is pretty strong, so nothing happens. And then right when the thaw happens, that material weakens again, but the pore pressure is still pretty high. And that might be one reason why we're getting pulses of a lot of material, especially where the springs are in that winter time frame, right? The strength of material is changing, and the stratigraphic or the hydrogeologic conditions are changing in a way that is triggering sedimentation. And he was able to catch some of these with his trail cams. We just put trail cams up that catch he caught a lot of animals too, but also failures. And so we were able to link those in time with the various pore pressure measurements that he was getting from his wells. So that's bluffs. So that's a sort of the generic system of the bluffs. And then some of the recent work that the students at Madison have been doing to try to help understand some of those things. And then we partner with Wisconsin Coastal Management and people like Andrew Struck at the Ozaukee County Park System, people who are trying to manage these systems to help them sort of think about what's going to happen or how they're going to manage floating staircases and things like that at Vermont, right? If you've been there. So again, I'll ask your questions. You don't have to have any, but if you got any questions or comments or stories that you want to share before I move on to beaches.
Well, I'm just curious, like, what's the purpose of doing all of these studies? I mean, are you looking at places where humans are going to have to intervene to keep the bluffs from continuing to degrade? I mean, all of this material would have been dumped here during the last ice age, right?
Yes. I mean, the original
so-
sedimentation was last ice age.
Yeah, so there's nothing naturally that's going to replace material that is being washed away. Is that correct?
Well, actually, that's what I'm going to talk about next.
Oh, okay.
Yep. Because, I mean, the bluff isn't coming back. Once you lose a bluff, that's gone. But sometimes these bluffs are called feeder bluffs because they actually they're the source of the sand for the nearshore system, for the beaches, ultimately, right? That's where they're coming from. And there is a lot of management decisions in terms of, and there have been management decisions and the consequence of those management systems that I'll talk a little bit about in the next section. As to like, why do we personally do this? The mission of the Geologic Survey is to collect basic geologic information that is then helps inform policy managers or policy decisions. So the Geologic Survey is not the DNR. We don't enforce anything. We're kind of lucky in that way, right? We're not the people who say this is what you have to do. We are the ones who people can turn to for information. All of our information is public. So, there's a lot of engineering firms that do this kind of work, but that's potentially proprietary information if they're private companies or they're doing it for a municipality. And so it's not necessarily shared. Our goal is to make information and data and about the Wisconsin geology in general public, right? That's our mission. And I see another hand. Yeah.
Yeah, Kay,
So
Kay
I
has a
have
question.
Yeah, so I'm Kay, and I was just, I've heard it said that the Corps of Engineers engineering has control of the water levels too, that if it's too much, they can take it out, or if they can transfer it to another lake, or is that true?
They can't, I mean, where there are structures, right? So if there's a
Yep, that's what
structure,
yeah.
they can open the dam more or less, but not in. So you can let more water in from Lake Superior partially, is my understanding.
Okay.
But the Wisconsin and Huron do not have a structure. They're wild. They're a wild lake. And if you look at Ontario, it doesn't fluctuate as much as the other lakes because it is really controlled system. And that's sort of good and bad because some of the plants that are along the shoreline have evolved to adapt to periodically being flooded and periodically being exposed. And so by not having that flooding and that variability in the Ontario system, there are some natural species that are not doing as well as they are in other places.
Okay.
But I should caveat, because we're being recorded by saying I am not an engineer, right? I don't work with the Corps of Engineers.
Yeah. Thank you.
Yep. Should I move on to beaches?
Sure.
Beaches. All right, so actually Mike gave me these pictures, right? So, what are the impacts on the beaches? And he pointed out, here's a beach. Mike, I don't remember if you told me which beach this was. This is in Sheboygan, right?
At South Beach, just south of Blue Harbor. You can see the Blue Harbor condos at the north side of both photos.
Yep. And that's so this is a case where clearly a lot of vegetation was cleared out. There may have even been some dunes that were cleared out. I know Point Beach, they lost some dune, sand, as well as the narrowing of the beach while the water was high, and then vegetation clearing out. And then of course you have a much nicer beach if you're looking to enjoy it after the water goes back down. So as I mentioned, the bluffs, if it was a natural system with no structures on it, they would be eroding and they would be providing sand for the beaches, which would then typically not just stay on one beach for the reasons I'm going to talk about now. So I'm going to do a little more sort of just like, what are waves and how do waves break? And then how does that impact beaches? And then how does fluctuating lake levels kind of are impacted by that? At least that's what I think I'm doing. Okay, so waves, obviously waves, when they come into the shore, what do we mean by breaking? That's when we mean they're tipping over and there's all that swash and foam that's happening. And that's something that happens as the beach or as the wave approaches the shore. But sort of why is that, right? Well, as we all know, there's lots of different size waves. And so the big waves, when they break, have a lot more energy than the small waves when they break. And they break in different places if they're big versus if they're small. So if you've ever looked, I'm sure you have looked at a stormy day off of Lake Michigan and the waves are breaking way offshore. And then on a calmer or a lower wave day, they're going to be breaking closer to shore. And so one thing I want to talk about quickly was just like what controls those wave sizes. And they're generated by the wind. It's the wind moving over the water that pushes the water and transfers energy into the water. That's what becomes the wave. So faster winds can make bigger waves. But for us in southeast Wisconsin anyways, it's probably more of this fetch, right? And fetch is just how long did the wind go over the water to transfer energy? So even a slower wind, if it's pushing on the water longer, will make a bigger wave. Or a set of waves. And for us, then any winds that come out of the northeast, right? So when winds kind of circulate and cycle this way, that's when we get those big 9, 10, 12 foot waves, the biggest ones that we sort of experience. And of course, I pulled up the surfing conditions and it's very poor today because the wind is coming out of the northwest. It's kind of slow, but it's also 14 knots, right? But it's coming the wrong direction. It's coming onshore from the offshore. It's moving offshore. And so that would make very flat conditions that are very poor for surfing. Of course, most people who surf in the world probably would say this makes it poor conditions. It's 37-degree water, right? What are you doing surfing up there? Anyway, that's one of the reasons why we get different size waves, and especially the waves that we experience. The reason they break then and why they break in different positions, either further offshore or in deeper water or shallower water, is the way that energy is transmitted through the water column. So I just got to talk about orbits a little bit, but if you're a particle of water, or if you throw a stick out there or something that floats and watch it, it'll just bob up and down if the wave's not breaking. If you're offshore and a wave passes, you go up with the wave and you come down with the wave, and you do it in a clockwise fashion. You make an orbit as that wave. So this particle is supposed to be the same particle going up and coming back down and basically landing in the same place. And the energy that is transmitted through the water gets weaker and weaker. So these orbits get smaller and smaller. And the distance that energy is transmitted down the water is about half of one of the wavelengths. So the distance between the crest of the waves, that's in general how deep that wave is felt. If you're swimming down here, you don't know that wave is going over you. If you're swimming up here, you go up and down in a circle. That's a particle of water or anything in the water. So as the waves come on shore, you can see them breaking here, but not breaking in deeper water, right? So they're only breaking when they get to water that's shallow enough, that kind of slows the bottom of the wave and tips the wave over, and that's what we mean by breaking. And then it can do work on the beach. It can either be attacking the bluffs or doing something to the sand on the beach itself. So this is just a picture from a textbook from Australia. But I like it because it really clearly shows that, we almost never get waves coming directly at us, perfectly straight, perfectly parallel to the shore. They're usually coming at some angle. And if they're coming at some angle, that means they're breaking on one side first, and they're not breaking over here. They're breaking later, and they're kind of bending. You can see these wave crests are bending, and they're actually pushing water down shore or along the shore. So there's a current of water moving in the direction of the waves breaking. And there's also then sand moving down shore as well. So the sand doesn't sit in one spot on a beach. It can get trapped in an embayment, but if you have a straight shoreline, every time a wave comes up, it goes up the beach face, and then the wave goes out and it comes down straight. It goes up at an angle, comes down straight. And we call that beach drift, which is all happening in that near shore area where waves are breaking. And you can see this quite clearly in places where we've put structures out into the water, right? So this is Cudahy, this is Sheridan Park, part of the Milwaukee County Park System. And these are some jetties that were put in, I think in the 30s, I want to say. And you can see that the beaches are wider on the north side of those because the biggest waves and the most sand movement happens when the winds are coming from the northwest. The other thing you can see, right? So jetties are a great way of trapping sand. And if you read that article from the Sheboygan Historical Society, you'll see that one of the reasons they put the jetties there was to widen the beaches, to provide more access to the shoreline for recreation. This also has in a bluff system, the effect of breaking up the waves, and that's why some of these were put in where there's steep bluffs to prevent the toe from being eroded. And so you can see it's a very stable slope right behind those. One of the problems with those is this is a system, though. This is a longshore system along the shore, and if we steal the sand here, we make these waves more erosive. There's not as much dispersion of the wave energy as it's coming towards the shore. And so you can see there's been quite a bit of erosion. If you look at 1930s photos, this is one straight shoreline. And since these were put in, this amount of material has been lost. Now, the Milwaukee County Park System is along the shoreline for that reason, because there was eroding shorelines, naturally. But this is exacerbated. If you look anywhere where there's structures immediately downdrift, so usually in the south in our neck of the woods, there's erosion problems. And so what's your solution? Your solution can be put more structures in. And so if you look at Racine and Kenosha County, I think Kenosha County is over 90% armored. There's a structure covering 90% of the shoreline. So you get basically concrete or jetties or some sort of revetment, just a wall, right? That's your beach for the whole system. And as you get further and further north, there's fewer and fewer of these, and we get more natural systems, right? Natural systems look more like this with hopefully a wider beach in some cases. Okay, so we want to, in this lake level fluctuation, one of the reasons, Laura, that we're doing it now is because we're in a lake level fluctuation. So that's a good time to study the impacts of the lake level fluctuations. We want to look at some of this as well for the beaches, and there are wide sandy beaches in Wisconsin. So this is Point Beach up in Manitowoc County, and so dunes. This is another drone picture. That's the lighthouse there, and sandbars. You can see the sandbars off the shore there. And so how can we map that whole system using modern technology, and some that's not quite modern, but at least we can throw into modern computer systems for modeling and such. So we can do the same thing. We can fly drones along the beach and get the elevation precisely of the beach. We'll get vegetation too, but we can do that. We can deal with that. We can go out into the water with a stick with a GPS, a high resolution GPS, and get precise elevation measurements of this portion of the beach. And then we want to map the bars as well. And we'll need some sort of boat for that. But these are shallow areas, right? These are, just a few feet and where the bars are. You can't really bring in a 15-foot Boston whaler or anything like that. You're really looking at something like a remote control boat, right? And so this is Chelsea, and she was the one who gave the walk. If you were on the walk, Chelsea was the one who led that for me. I was originally going to do that, but she's now doing her PhD with us. She did the seasonal, figured out that December was the time that or just after the thaw was when most of the erosion was happening in the bluffs.
Dr. Rawling,
Yes,
sorry to interrupt, but is that the boat that went on the Great Adventure?
I was just about to.
Okay.
That's the next two slides. Yeah, that is the Great Adventure boat that you may have heard of. And what it is high resolution GPS, a laptop, and then a sonar. So just like a fish finder, except a little higher resolution. And it's all connected so that every time the sonar hits the bottom, estimates the elevation of the bottom, we know exactly where we are because we have a really high resolution, several $1,000 GPS unit on it. And there's Chelsea sending it out. And what she can do then is go in that really near shore area that most people don't study. There's not actually, we don't have a lot of information of how the bars behave, because you need a boat, you need a remote control boat, you need these cheaper high resolution GPSs that are now available in order to do that. And so this is at Lion's Den, and it's the same kind of thing. She's doing transects, collecting elevation of the bottom of the shore, and then figuring out the difference between two surveys. And the other benefit of this is we can do it when it's cold. So we had one of these rigged up to a John boat that we were doing, but you can't really get the John boat to every site. And then you've got batteries maybe, or that you're dealing with, and you might tip over if it's in the winter or just after the winter. And so we got this remote control boat, but that was the one you may have heard of, Laura, where there it is going off. This isn't the day. This was me taking a picture of Chelsea on a different survey, but we were going out, 300 meters, so 600 feet is 700, 1,000 feet ish. And she lost connection with it when it was pointing in the wrong direction, and it just kept going. Right? And so you can Google, missing research boat, Lake Michigan, and you'll find a whole bunch of news stories about it on the local news. It made the local news. It ended up in Michigan. It went all the way across, and sort of on the northern part of the Lower Peninsula, somebody found it, and while he was hunting, he found it about a month after we lost it, but he had like a medical issue while he was pulling it out of the water. I think he had a stroke. And so then his friend was visiting him, and he told his friend like a month later, yeah, I found this boat, and his friend was an engineer, and his friend called us, And his friend happened to live in the town that her main professor grew up in, or her brother-in-law was. And so we got the boat back. But unfortunately, she was chasing a storm. There was a storm right before that she had surveyed the bottom of before the storm, and she was going to survey after a storm. And but we lost the GPS, and we were able to recover some of the data, but we don't know where in space it was. So she wasn't able to use that data. That's the incalculable loss, because this whole rig was $10,000, which is a lot of money, but not hundreds of thousands of dollars. All right, so we're starting to study the bars. I don't have a lot of results because Chelsea's still in the middle of that as part of her PhD, but I just have a little bit of ice to talk about as the next topic. And I know we talked before everybody joined, but we had, there's 2 hours budgeted, but I have about an hour of talking and any discussion that occurs with it. So any questions on some of that nearshore stuff or the beaches? What we're really trying to do with Chelsea is, can she model, using some data that we're ground truthing, what happens when the lake goes up? If a big bluff failure happens, where does that sediment go? How long is it residing? Are the bars residing? And one of the results that one of the things she's thinking is happening is that the bars typically aren't moving very much. They don't really come on the shore. If they do get on the shore, they go back off the shore because we have such a wildly variable lake level, even on the scale of, these 10 years, but seasonally, as well as these storms, as well as the seashes where the lake level kind of goes up and down. So because we have a pretty messy system, the bars are relatively stable, although sand is moving down the shore potentially. So it's not always the same sand in the bar, right? But the bars seem to stick around the same position over time. That's preliminary. I see one hand up.
Can you hear me now?
Yes.
The sand, Chelsea Volpano, she did such a wonderful job at that walk, that geology walk. And I was shocked to learn that our sand can travel south all the way to Illinois. So
Yes.
does sand travel in the same direction? Is it always south? Does it always travel south?
Well, we can get big waves that go north, but most of the big waves come from winds that are coming southwards, right? And so the dominant transport is to the south. There are times when it goes north, but overall it's going south more than it's going north.
Oh, okay.
So it's not 100%, but it's on average. And ultimately that's the way it goes.
Okay, thank you.
Mhm. Anyone else, or should I move into ice? I'll move into ice. Okay, this is another thing that we're kind of interested in and have been studying with the students at the Madison campus with Luke Zoot is the professor that manages them for the most part. And then my role is to help them in the field and then serve on their committee, help them write their research up. But the last one is ice. And of course, when you have ice, you can see it can provide a barrier to any waves. So our winters tend to be the stormiest season with the biggest waves in the Great Lakes and in southeast Wisconsin. And that can be buffered by the waves breaking up against big ridges of ice rather than just along the shore, a bare shore. And so, but if you read the surveying literature and the engineering literature about ice impacts, there are some people who suggest actually it causes more erosion. And so there's some debate about what ice does. And of course, if you're in years like this, where there's very little ice, right, then there's no protection at all from it. And so it's a thing that's becoming more variable in the southern Great Lakes and maybe even more variable in places like Lake Superior, and so because ice is hard to study, it's really hard to do field work in the winter. It just hurts and it's challenging, right? It's cold out. there's a lot of cold coasts, but those ocean cold coasts are even harder to get to and harder to study. We've been trying to use the Great Lakes as a natural laboratory to look at places where there's more variability in the ice. And does that cause more erosion versus where it's more stable? Is there less erosion? And so how are we doing some of that is what I'm going to talk about in this section. So just a picture from the Journal Sentinel in Wisconsin. This is up in Lake Superior. And so these ice zones along the shore are called nearshore ice complexes. And there's this is Lake Superior in Bayfield County. This is some people in the back. And this is a real typical what you see along these is that there's freezing right to the shore face in a frozen foot, if you will. And then there's usually flat areas. That's what we're standing on back here. We're off the shore where there's water below us. And then there's these ridges that kind of pin along sandbars typically, or maybe wavy conditions, rake a ridge. And then sometimes there'll be more of these. There'll be another flat area and another ridge. And there could be 2, 3, or 4 of these, depending on the embayments, shape, the amount of waves that come in, any storms that come in can break some of this up and reform it, or how cold it is that year. And so we've been doing a number of things to look at some of these systems, including getting out there and coring through the parts that are frozen and trying to estimate how much sediment is actually frozen to that, and where would that break, and how much sediment would you be able to move off if you broke this all up really fast. Some people have suggested that when the system breaks up, it takes sediment with it and drifts it out, and then it's lost because it gets in deep water. We think that's very rare and maybe something that happens under very special, a very fast warm up, and then a big storm would have to move everything off sort of at once. The other thing we did is build this wave tank. One of our students, Stephanie Dodge, so there's a plunger over here, and the waves are here, and this is in a cooler, and so we can freeze it, and we can model frozen beaches and kind of compare that to some of the observations in the field. And that's a challenging thing to build and do as well, sit in a cooler. So that poor student had to just sit in a cooler all the time in freezing conditions. And then we're combining that with sort of similar shoreline observations with drones and these remote control boats, because we're trying to get out there and survey just before the ice goes on, and then right after it comes off, before there's a big storm. And that means you got to be ready to go, and you have to have a team of people. And one of the team of people that we're working with is Ethan Tierkoff, who's a professor at Michigan State. And so he's a coastal geomorphologist. He studies these systems. And he's been doing most of the field work on some sites in Michigan for that. And what he noticed when he was doing that is that if you fly a drone over it, you'll see these scours offshore that are at the same position that the ice was. So this is sometime after the maximum. There's ice was all the way out. This is where those scars were, and there was ice all the way out here. And then this is just 5 days after the ice comes off, and then there's this scour surface here. And so we worked with the wave tank to build an ice complex, and then watch how sand is moving or interacting with the waves against a model, a sort of scaled version of this. We have these sites, and then we're working on some computer modeling. Chelsea's working on some computer modeling to kind of try to figure out what's going on here to make these scours. And what we've come up with is that if you have a ridge that's grounded or close to the ground, and the ice front, basically when big waves come in, they interact with that, and that energy is pushed further down than it might be otherwise, and you're scouring in deeper water. And you have the potential then of scouring this material out into deeper water, which is called the depth of closure. That ultimately you get to a point where you're deeper than the biggest storm waves, and you'll never get that sand back up on shore. And that might be what happened back in the polar vortex, I think it was 2014, but like when we had those that really cold year, and it was still low water, and we had big ice complexes, and they lost a lot of sand in the sort of Kenosha County, Illinois border area. And this is potentially one mechanism. So if the lake is low and there's a big ice year, you can push that sand off. And then if the lake comes up, that sand is lost. That sand is out there in deeper water and unavailable for being pushed back into the bars, which ultimately can go into the beaches and be part of that nearshore system that is then fed by the eroding bluffs, if there are eroding bluffs in the area. So that is still pretty preliminary too. Chelsea's working on that, and we have a few papers out on some of those pieces of the ice stuff. But like I say, that's still sort of a work in progress. So this is Point Beach. This is the picture of Point Beach from above with a drone, where the stream comes out, and back before the lake went up. And I just want to say, some of the work that I've been talking about is funded by Sea Grant and the Park Service and the survey itself, the Geologic Survey. And there were a lot of papers that I didn't cite, but there were some research papers that have come out of this. And if you're interested, you can email me and I'll send you copies of those. Or if you want to talk more about some of these studies, or if you think that there are issues that could benefit from some research, we're always interested in that and other potential collaborations going forward. So with that, I'll say thanks for listening, and we can open up for a general discussion. And I'm pretty sure I talked for about an hour.
Yeah, it was perfect.
All right. Go ahead.
Yes, the North Point Bluff, it certainly is interesting. There's a clay, it's clay and sand, I believe, and it's full of seeps. There's a lot of natural seeps, which is very interesting. They're constantly draining. In the wintertime, it all turns to ice out on the road. But there is a couple of places on the bluff that have slid, or I want to say they've slid down close to the road, like all the way down to the gutter, and at some point, is that going to keep sliding and eventually creep out onto the road? And what can be done about that? I mean, it can't encroach on the road, obviously, but is that erosion a very slow process from the seeps?
Yes, and I think I don't know what the actual composition of the bluffs are. You can look at wells, or you can look at old pictures, or there might be some exposures, but typically the stratigraphy in the Southwest is some sort of layer cake, where there are some, in this case, so you can imagine this is that bluff. This is a clay layer, and then there are sandy layers, and this might be a silty layer. Mm-hmm. And the water will get hung up on those clay layers. So if there's a layer at the bottom that's more clay rich, any water that percolates in hits that and starts to move out, and then it comes out on these springs or seeps, right? Or because sometimes they're not really focused areas, but they're just wetter areas that are intermittently along the shore, or the bluff. And some of that, where those are located, is related to how these sediments are fractured. So sometimes these sediments even have fractures in them, and water can preferentially move down the fractures. And to answer your question, what can be done? It does move into that basic geology thing that I just talked about, into more of a engineering site-specific study, right? And so if there's more water coming out, it could be that there's a year where it freezes more and that seep is plugged up, and then we get some release, and then there's a little bit of erosion associated with that. Or it could be that there's a tree tips, and we have more sort of concentrated erosion that's very shallow, but happening, right? It's not like deep seated where this whole thing fails, but we have just water running off of that bare surface, and that can move material down. And then the whole thing does move slowly. Typically, slopes move down from freezing and thawing, or just getting wet and dry. The upper sort of 3 feet of the soil will expand and contract and expand and contract and move very gently down too. So
Mhm.
what can be done is letting that slope get more at a natural angle, right, that it wants to be at. But obviously, we also have things at the toe of these slopes that we sometimes can't allow for that. And ultimately, then it becomes some combination of land use decisions about and policies that concern people at the base, maybe roads, or people at the top with either infrastructure, sidewalks, roads, or houses, right?
Mhm.
But slopes fail. That's what they do.
Yeah. Interesting. Thank you.
Part of the problem, where Star is talking about too, is also because of structural things at the top, like
Yes.
homeowners putting their drainage down the side of the bluff, and also even just the road being there, which is a hard surface, which then runs off, down the bluff in an unnatural kind of way.
Water
And
management at the top of the slopes is crucial, right?
so that is hopefully going to be addressed by Stan Tech, who is designing some rain gardens and also at least one bioswale for that area. And then there was some places where they put the drainage, like drainage pipes coming off of like
Storm
homeowners'
drains, the
land.
storm drains, yeah.
Yeah, going down the side of the bluff. But then they also put I don't know if it's called riprap, and that's but they piled rocks and stuff.
Right.
So that's all going to be removed, and that's going to be kind of rebuilt somehow. I don't know exactly what it's going to look like, but it's going to be interesting.
Yes, and that's kind of what I mean by it becomes engineering and a site specific. What is actually going on at this site to answer, your specific question, Star? Because there are so many variables: land use, natural stratigraphy, natural processes, and all of those things sort of combining.
Well, if there aren't any other questions, I want to thank you, Dr. Rawling Elmo, for joining us. This was really interesting. It's a lot of information to kind of absorb and think about. That is really, really interesting.
Yes, thank you. Very
Yeah,
interesting.
Very interesting.
Thank you. This was great.
Well, no, thanks for having me. This is our part of our mission is outreach, and so we are happy to do these events. And if they're, like I say, you can feel free to share. I'm supposed to say, I forgot my caveat. We are supposed to now say there are some groups that were charging memberships for people to get to a website to see some of the presentations. So we're just supposed to say information we provide is public and free for the public to use. And if there's an organization charging for it, that is not because of the state geologic survey. But feel free to post it or share it, or I don't know, Laura or Patricia, if you want me to email you a PDF version of this, I'm happy to do that too.
Yeah, I would love a PDF version as well for us to put on our website. And then I will get this uploaded onto our YouTube page as well. So
That's great. Well, if you do, please just maybe send me a link if it's public, because then we'll put it on our social media and again, get some visibility that way.
Great.
absolutely.
It was worth fiddling around with my sound system to get this to work.
Good, Mary.
I want to thank Patricia too for setting this all up for us.
Yes, thank you.
Absolutely. Like I told you, I love it. So I'm glad I was able to help.
Yes, well, thanks for joining on a nice Saturday, and
Yes.
enjoy the rest of your weekend.
You
Yeah,
too.
Yeah,
thank
you
you.
too.
All right,
Thank you, everyone.
Bye-bye.
Thank you.
Thank you.
All right, bye-bye.